In this problem set, we're going to be looking at a bunch of problems related to section 19.5, looking at numerical integration and differentiation. In this first set, we have 7 different problems related to this single set of data shown at the bottom right of the screen. The first 2 problems deal with integration. Problems 3 through 7 deal with differentiation. So starting with integration, we're going to integrate across the set first using trapezoidal rule. So problem 1 looks at the trapezoidal rule. So there's our problem set. And to apply the trapezoidal rule, you can find that formula in the notes or the textbook. But we simply use the trapezoidal weights, which are 1/2, 1, 1, 1, 1, 1, and then you get to a half at the other end of the data set. You multiply f of x times the weight to get the product of those two. You do that for your entire data set, sum them up. In this case, we get a sum of 48.5. Once you have that sum, you multiply by the interval size, the size from one x to the next, and we have x's that are spaced 1 apart, so h is 1, so that sum times 1, our integral is just 48.5 by the trapezoidal rule. Now the slightly more accurate, or the significantly more accurate Simpson's rule, when applied to this same data set, should give us a better answer. And so we now apply it using the Simpson's weights, which are 1, 4, 2, 4, 2, 4, 1. And remember, we have to have an odd number of points. So if you look, when you count from x equals 2 to x equals 8, 7 data points, we can apply the Simpson's rule. So we now have we calculate the product again with f of x times the Simpson's weights to get the product, sum those up, and when we look at this formula now, we take the interval size h divided by 3, and we get the slightly improved estimate of 48. And my f of x here is actually a third order polynomial, so it just so happens that this is exact. Simpson's rule is going to give us the exact answer in that application. So there's a couple example of integration. We'll have a little bit more later in this slideshow. In problems 3 and 5, we're actually trying to estimate the same thing, but one time we're using a 3-point rule, the other time we're using a 5-point rule. So in problems 3, we're using the 3-point rule, equation 14.b in your text. And in this case, we use, since we're looking at f of x equals 4, f prime at x equals 4, we'll be using the data at x equals 5 minus the data at x equals 3, and we don't even need the information at f of x equals 4. We just use 1 to the right and 1 to the left in this equation. And then when we just complete the task, we have h again is 1. So we end up with a slope at f of x equals 4. At x equals 4, the slope is 3. In problem 5, we're using 5 data points, 2 to the right of our observation and 2 to the left of our observation. So the slope at the center, or at point 2, involves this calculation, and when you complete it, we get a slope that happens to be exactly the same, 3. And it's because I used a relatively simple function that we're getting exact answers here, but we should get the exact answers if we're doing this right. So 3 and 5 both related to the slope at 4. In problem 4, we wanted the second derivative at x equals 4. So in this case, we have to use one point to the right, the point at the x that we're interested in, and this is f to the right, this is at the point, this is at the left, and now we're dividing by h squared in this application, and we get a second derivative at x equals 4 of 1. In problems 6 and 7, we're using what are called one-sided formulas. We're looking at the information at the left side of our data set, where x is 2 in problem 6. And in problem 7, we're looking at the right side, where x is 8. In these cases, we have to use the appropriate formula. So at the left side, it's 14a. At the right side, it's 14c. And we have a 3-point formula in each case, and you'll see which data is being used here, and we just use the appropriate formula, and we get the slope at the left side of 1, and in problem 7 we get a slope on the right side of 7. I have a few more problems where I'd just like to repeat some of these tasks. This time I wanted to do something a little different, and that is I used a different interval size. So now you'll see that my interval size is 1/2. And I also added some units so that we can see how units affect our results. So in problem 8, we're going to look at integration, and in 9, we're going to look at the derivative. So integrating in 8, and we're taking the derivative in 9 and 10. So in 8, we're using Simpson's rule again, and it's actually the same function that I used to generate this data set. So you've seen those numbers before, some of those numbers before, but we use the same Simpson's weights, 1, 4, 2, 4, 2, 4, 1, and we again have 7 data points, so we're able to use Simpson's. It's an odd number again. And when we get the product and sum the product, we get 162 feet, because remember depth was in feet, so the weights have no units on them, but the product would have the units of feet, so that when we sum it up, we get 162 feet. So that when we calculate the derivative, it's sum times the interval size. Well, our distances were also measured in feet, so h is 0.5 feet. So in fact, when we take our sum, 162 feet times 0.5 divided by 3, we get a total of 27 feet squared. It's not terribly surprising that when you have two things, distance and depth, both in feet, that we're really getting an area. And yep, we're getting the units of area when we integrate as well. Now let's look at the derivative. In problems 9 and 10, we're asked for the derivative on the left side in problem 9 and in a centered formula in problem 10. And now that you'll see that we again have the interval size is 0.5 feet, and that our function is actually measured in feet, but we end up in this case with feet divided by feet, so we get a slope that's unitless. And here I said it's 3, but I probably should have said 3.000 and reported 3.000 as my answer, so that I had the same number of digits that I had in the original data set. And I did that properly in problem 10, where I'm using the centered formula to find the slope at x equals 5, I believe, and there I did get a slope of 4.000 as my result. Again, the units are units list because it's feet over feet. Hope those example problems helped. Good luck with this week's quiz.